And I'm starting the recording, just so that I don't forget to do it when it's time, which I have done several times already. So, all right. Are there any questions about the stuff that we have talked about? Nope. So the notations are good, logical operations, and we have talked about all the way to set intersection operation, I think. And we haven't talked about union yet. All right. All right. Has anyone tried the GPT TA? Not yet? Okay, well, that's fine. When it is time, you can go ahead and check it out. Oh, right, because I wanted to try my router. This time it connects. Okay. Oh, the nice thing about using the route, being able to use my router, is I can now use my tablet. Okay. Well, we'll see whether it works here or not. So it's 10:36, D7, 8. Nope, it doesn't work. Well, I'm gonna have to figure out why this is not working another time. Hmm. All right. Well, it is 3 o'clock. I'm gonna get started here. It's already recording, so I just have to point back to my notes. And this time around, I am going to use the hair splitting version. Okay, there we go. And we are just thinking. Okay, maybe go back to use the more spelled out version here. All right. So last time we talked about intersection, which is this particular symbol here. And today we are going to move on to union. So this is a continuation of the stuff that we talked about on Monday. And you can see that the only difference between intersection and union is the logical operator. So with an intersection, it is defined as E is an element of A intersecting with B if and only if E is in A and E is in B. In the case of a union, the only difference is switch that conjunction with a disjunction. So in the case of a union, an element is in A union with B if and only if E is in A or E is in B. So if an element is in one or the other or both, then it is in the union. So do we have any questions about the concept of a set union? Okay, if there are no questions, then we are going to move on to difference. So this is the definition of difference. The difference between set A and set B would be all the elements that we can find in A, but not in B. All right. So we're still okay, doing okay with the set operation, okay, what looks like a subtraction, it is called difference. All right, so we move on to um, what looks like multiplication. So this one is a little bit special and will take a little bit, it will take a little bit longer. And I'll give you guys examples, after, talking about the symbols. So it looks like multiplication is called the Cartesian product. The Cartesian product is a little strange because instead of having single elements that's either from A or B or both, each element in the Cartesian product is what we would call a tuple. Okay, so when you see xy inside parentheses, it is called a tuple. The closest thing from CISP, 360, 400, and so on, to the concept of a tuple is an array. So in this case, we have an array of two elements. Okay, the first element of the array has to come from A, as specified here, and the second element y has to come from B, as specified here. Okay, so this one I think we actually need a few examples to illustrate how it works. So I'm going to give you guys some examples to work out, and then see if you can kind of apply the definitions to figure out the answer to these questions. All right, so we are going to specify a set that has A, B, C in it, and we'll do the Cartesian product with another set that has the numerical values 1 and 2 in it. So now the question is, what will end up in the actual Cartesian product of these two sets? What do you think? Okay, so I would just go ahead and randomly pick something, and you tell me whether it's going to be there or not. Okay, so what about the tuple that we call D and 5? Do you think that is going to be an element of the Cartesian product? Nope, it's not, because I don't think the set ABC has D in it. I don't think the set 1, 2 has the 5 in it. So, nope, this is not going to be one of those elements. Okay, get rid of it. What about 2C? Do you think 2C as a two tuple is an element of the Cartesian product of the set ABC and the set 1, 2? Nope, it is not, because 2 is found in the set of 1, 2, not in the set of ABC. So this also does not meet the criteria. Okay, or I should say the two tuple, 2C, does not meet the requirements to become a element of the Cartesian product. Okay, so that doesn't work. What about if we switch the order? What about C2? Do you think that is an element? Yep, it is, because C comes from the set on the left-hand side of the operator, and 2 comes from the set on the right-hand side of the operator. So this is one of the elements. So what else is in there? Okay, so I'm trying to be as unstructured as possible because I want to emphasize that there's no intrinsic ordering of elements inside a set. So we can just keep going like this. A2 is not there yet. What am I missing? B2, that's right. Thank you. So there are 6 elements. There are 6 elements in the Cartesian product because there are 3 elements to the set on the left-hand side, and there are 2 elements to the set on the right-hand side of the operator. Yep, that is correct. Because in the tuple, order does matter. Hmm. I forgot the A1. Oh, because I got two A2s. Okay, so that is my mistake. You cannot have 2 elements of exactly the same value. So between the A2 and A2, one of them has to be the A1. Thank you. All right. So now the next question. How do we know that elements or the order of elements in a tuple is significant? How do we know that? I can have two answers to this question. I'll give you the obvious one. Read the reading material and you'll find that out. Okay? So please read the reading material. Okay? It is I did not write it just so that I have it. Okay? I write it because I want you guys to read it. Okay? So that's important. In fact, I can just point it here. Okay, so it is ordered. So so the fact that it is ordered means order matters. So that means you have to um so AB as a two tuple and BA as a two tuple are considered different because it is an ordered container. All right, and it may contain duplicate values. So that means you can have a two tuple with 1 and 1 as the two elements in the tuple, but you cannot have a set with 1 and 1 as two different elements in the tuple. Okay, because all elements in a set, you can only have up to one instance in the set. All right, are we doing okay so far? All right. So now we're gonna take a look. Well, let's go back and look at some examples. Okay, so when we're gonna go back and look at the examples, and I'll give you guys, like, some of the tests just like here. So I will give you something like, what is the empty set intersect with the set of, 2, 3, and 4? I cannot really do the intersection symbol with a text editor. If you want to, I can actually do mathematical notation using a program called an app called Joplin. So if that is good to you guys, I can do so as well. Okay, but yeah, I mean, for something like this, it's not too critical. So what is the result? What is the intersection between an empty set and the set that has 2, 3, 4 in it? Is the empty set itself? Yes. So to be more precise, it is the empty set. Why? We go back to the definition, yes. So we go back to the definition. An element, a value, is in the intersection of two sets if and only if that element is in the first set and the element is also in the second set. Because of the conjunction, because of the use of the conjunction, the and. So that is why, when the one of the two sets in the intersection is an empty set, the result is going to be an empty set. So in this way, the empty set is kind of like zero in algebra, and intersection is kind of like multiplication in algebra, because 0 times whatever is a 0. In this case, the empty set intersecting with any set is the empty set. So it has kind of the same property like a 0 in multiplication. Are we good? Doing okay so far? All right. All right, so we'll take a look at another example. What about A, B, C intersecting with 1, 2? What would be the result of that? It is also an empty set. Very good. And then we go, what about A, B, 1 intersecting with B, 2, 5? Just B itself. That is correct. Okay, excellent. So now that we are done with intersection, let's try union. And I'm super lazy. That's what I'm going to do. So we'll turn all the intersection here into union, and we'll work on these one by one. So what is the answer to this question? We have the empty set, and I want the union between the empty set and the set that has 2, 3, and 4 in it. What is the result? That is correct. All right. So from this perspective, you can also see that the empty set is kind of like doing the job of 0, except in this case, the union operator is kind of doing the job of addition because 0 plus whatever is whatever, and it's doing the same thing over here. Does that make sense? All right. So now we move on to the next one. Okay, so now we want to look at the union between these two. So what would be the union of the set that has ABC in it and the set that has 1, 2 in it? All right, yep, but I'm going to scramble things around a little bit to emphasize that order does not matter. There we go. All right, so this is our last one. Okay, do an intersect here or change the intersection to union. All right, so what else should be in the answer? Yep, there you go. Cool. Are we ready to move on to difference? What looks like a subtraction? Okay, so let's do that. All right. You can see how laziness actually get me a long way. All right, so for this one, I'm gonna change the order a little bit. Okay, so that's it. All right, well, we'll do both. How about this? We do both. All right, so we'll put that over here. All right. Okay, so we'll work on the first one first. What is the difference between the set that has 2, 3, 4 in it and the empty set? In other words, I'm asking what is on the left-hand side, but not on the right-hand side. Yep, so in this case, it is just 2, 3, 4 itself. Very good. So 2, 3, 4. What about this one here? It returns the empty set. That's right, because there is nothing that is in an empty set that is not in the other set, because there's nothing in the empty set to begin with. Done. All right. So now we will kind of do the other two. Okay, so we'll change this one to a minus, and then you guys can tell me what the answer is. That is correct. It is A, B, and C because all of A, B, and C are on the left-hand side, but not on the right-hand side. All right, so one more. Okay, so this one was the union, but now I'm turning it into difference. So what would be the answer to the last one? That is correct. Because B can also be found on the right-hand side, so it cannot be a member of the difference. All right, excellent. So that is, I think, a good practice of these concepts. Are there any questions related to what we have talked about up to this point? They're not too they're not too difficult. You just have to remember how things are defined. All right. So now we're gonna move on. Okay. It's kind of hard for me to juggle between those two screens because this room is set up a little bit differently from the other classrooms. All right. So we are gonna move on, and we are gonna talk about this is called subset of. So the way we read this is A is a subset of B if and only if the difference between A and B is an empty set. And the intersection between A and B is just A. All right. Are there any questions about that description? It's not the only way to describe A is a subset of B, but it's one way to do it. Are we okay? Yep. All right. Yes. A is a subset of B if and only if the difference between A and B is an empty set and the intersection between A and B is just A. All right. So we are going to try some examples. Okay, so we'll go ahead and see if certain things are subsets of each other or not. So I'll give you some examples. All right, so I'm going to try something that is, we'll start off with something that's kind of funky. So we'll start with the empty set, and we'll say is a subset of the set of, that has A, B, C in it. So what is the answer to that question? Is the empty set a subset of the set that has A, B, and C in it? So, okay. Mm-hmm. Mm-hmm. In, yep, with anything, the empty set. In fact, all of those examples were things that we have worked out before. Okay, so this is true. Okay, so it doesn't give you a set, it gives you a Boolean answer of whether it is true or not. In this class, I'm going to use 1 to represent true and 0 to represent false. All right, what about the other extreme case? What about A, B, C being a subset of A, B, C itself? So is it true or false? So when you think about this, don't try to think about it from the semantic perspective or try to guess, what the semantic, meaning is. Instead, plug it into the definition and see what you get. So the first question is, what is ABC minus ABC? ABC being a set that has ABC in it. It would be the empty set, right? Because ABC, every element in ABC can be found in ABC. So as a result, the result is the empty set. Okay, it meets this requirement. The next question is, what if I were to intersect the same set? So ABC intersecting with ABC, what do I get? The set of ABC again, right? Because every element in one is automatically in the other one because they are the same. So that means it would be this requirement too. This conjunction is going to be true, and that means a set is a subset of itself, always. All right. Okay, so we put a 1 here. So now we look at something like, what about A, B2 being a subset of A, B, C? It is false, but we want to know why it is false. In this case, AB2 minus ABC is, yeah, exactly, it returns a set of 2, which means this equality is false. And because this equality is on the left-hand side of a conjunction, that means I don't even have to bother to look at the other side because, false and whatever is always false. All right, so we just have to write down the answer like so. And then the last one is kind of like an easy one, but I'm going to put it here too, just so that it is clear. What about that? Okay, it is true. Okay, because you have the plugging in. So the first question is AB minus ABC, is it an empty set or not? The answer is yes. And then the other one is if I were to get an intersection of A and B, in this case, A is the set that has AB in it, and B is the set that has ABC in it, the intersection is the same as the set that only has AB in it. So as a result, the answer is true and true, which means the whole thing is true on the right-hand side of an if and only if. If the right-hand side of an if and only if is true, what is the left-hand side? If I tell you the if and only if itself has to be true, and I already tell you the right-hand side of the if and only if is true already, what has to be on the left-hand side? It has to be true. That's correct. That is correct. And when did we learn that? Monday. That's right. 48 hours ago ish. So if this is, if you're not remembering those things, well, what do you think we should do? You might want to take notes, okay? Because taking notes help you remember things. Doing some exercises can also be helpful. And reading the content, is always going to be helpful as well. So try to do all that. Yep. hmm So are you talking about the Boolean operator or are you talking about the set operations? Just the Boolean, right? Okay, we can take a look. So we are talking about Boolean operator and the exercises at the back, right? Okay, so do you want to pick one as an example? The third one, this one? Okay, all right. All right, so I want to know the truth table of this. Okay, so the first question is how long is that truth table? How many rows do we have in that truth table? What do you think? Hmm? No. Nine-ish if you include the header. So the truth table has 8 rows in it. Okay, because Q is Boolean, so it can take on the value of 0 or 1. Same thing with R, same thing with P. Is that correct? All right. But when Q is false, that doesn't change the value of R or P. So that means when Q is false, R can be false or true. When Q and R are both false, P can also be true or false. So in order to understand why there are 8 rows, the best way is to the best way for me to do this is to illustrate it in a certain representation. If I can find a marker first. Why do we not have? I can do it in a in a text representation, but I would rather do it here. Well, I guess since I don't have any dry board markers, which is really odd. hmm Well, you want to cover all the cases, and a truth table is an easy way to look at all the possible cases, and then you just think about, okay, am I handling this case? Am I handling this case? And so on. So I can do this without, a dry, a whiteboard. It's just going to look a little bit messy in just plain text, but it's doable. Okay, so let me. Oh, okay, I just lost track. We're looking at that one. All right. So we're looking at Q, R, P as our variables, and then we're trying to evaluate Q if and only if R and P. Okay. Or in the shorthand that I'm talking about, it's just RP. When did we learn that R and P can be shorthanded into just RP? Monday. That's right. So you guys have to kind of you have to stay on top of the notations, okay? Because otherwise, if you don't study the notations in the following class, I'm using those notations sometimes in the same class, and that will just make it really hard for you to understand what is going on. All right. So when Q is false, R can be false, and then P can be false or true. Does that make sense? Okay. So what about I keep Q to be false, but R is true this time. So this is false, this is true. Once again, P can be false or true. Does that make sense? And then finally, if Q is true, then I can make R false and P also false, true, false, true, and then we have false, true, true, and then false, and then true, true, and true. Yep. Can you be more specific? Yeah, it's just harder for me to fill in the table that way. But I know what you're talking about. So what he's talking about is fill in the four zeros here first, and then the four ones over here, and then the 0, 0, the 1, 1, copy and paste over here, and then the 0, 1, copy and paste over here, and then copy this entire pattern and paste it here. So that's a quicker way to generate the truth table if I was using a spreadsheet. But since I'm using a text editor, it is line oriented, so it's much harder for me to do it in a column way. All right, so these are the 8 possible cases. So the truth table just says, okay, evaluate every single one of these possible cases, and tell me what the answer is. All right, so we are going to work this out. Okay, so in this case, the answer is true, and in this case, the answer is also true. The answer is true. The answer is false. And I think with this one, it is false. This one is going to be false. This one is going to be false. And this one is going to be true. No, I did not look at the answer. I did not, have the answer like on my palm. I just evaluated the whole thing really quickly. Okay, because RMP means conjunction, right? And this is just Q. This is if and only if. So on the first row, we're really asking false if and only if false and false is what? Well, false and false is false. So the whole thing boils down to what is the result of false if and only if false is true. Exactly. So how do we know that? The truth table that we talked about on Monday. So this is about the application of truth tables, which actually just define the operator. You don't even have to know what does if and only if mean. Oh, don't care. If it is this operator, we look up that particular truth table. Okay. So the next three are all ones because between R and P, at least one is a zero. So that means the conjunction is going to be a zero. And all the first four rows have Q being false. So that means, on the first three rows, the right-hand side of the if and only if is going to be the same as the left-hand side, which are all zeros. The fourth row is going to be a false because when R is true, P is also true. Then we have true and true, which is true. But since Q is also false, it's still false. So now we have false if and only if true. And if you look at the truth table, that will give you an answer of false. Now I can do this relatively quickly just because, I can read the notation, with some proficiency. And I also know the truth tables already by heart. So I can do this really quickly. But, with some practice, you guys can do the same. I mean, this is just table lookup. Um, it's not broken. This is all good. Yep. I think I fixed that, and then I fixed all the generated questions. Yep. So do we have any additional questions about these cases? So I better double check to make sure the answer is actually correct. Because that would not be. Oh, look at that! It's broken. It is still broken. Darn it. Okay, because this is supposed to be a one. Ah, okay. This is supposed to be a one, two. This is supposed to be a zero. Okay, I have to fix it. I'm sorry about that. So I have to fix it. Ah, okay. My bad. My bad. What? Yeah. Yep. Okay, that is definitely my fault. But given that that is my fault and your answer is a little different from what is displayed here, so in the absence of this class or me, what are you going to do? How do you double check your hand generated answer is correct? ChatGPT is one. Okay. What else? You write a very short program in C to do this. So the question is, how short of a program is that? Well, I would do it with a triple nested loop, one loop for each variable, but they're all nested. So by the time you get to the third or the deepest level of the loop, you just kind of implement all those operators and print it out. Okay, so that's a fairly quick and easy way to you know double check the answers. So what is in my mind right now is what is the bug that I have in my program that got this wrong? So I'm already thinking about that because the only two rows that are wrong are these two. So let's see. Are these two? They are flipped basically. Nope, it's this one and this one over here. So these two rows are wrong because I want to know why things do not work. Anyhow, so I do apologize. This is my mistake. It is still wrong. So, Daniel is correct. I have not fixed the bug yet. All right. Any other questions? Nope. All right. Yep. hmm Well, I'm going to give you guys some homework, today, but it depends on whether I can finish all the topics that I need to finish. So I don't know yet whether we can do that. But one thing I'm going to do is to take roll today because I forgot to take roll on the first day, which is Monday. So I'm going to take roll today, and today is the 27th. So I just have to unhide this, go here, and you can do this on your cell phone or your laptop computer. It doesn't matter what you do. And the access code is implication. If you're using a cell phone, kind of make sure that you're on the school Wi-Fi network because I'm putting an IP filter on this too. I suppose. Well, they will be counted as being absent, that's for sure. But everybody has an allowance of 5 absences, and that's plenty. So if they did not learn from the first two or three absences and kept going, so are we doing okay? Does everybody get a chance to kind of sign in and report that you are present? Okay, all right. So we haven't even gotten to the good stuff yet. There's some pretty good stuff. So we're gonna go back here. Not this one, but we go back here. So this is subset of. And this one is called proper subset of. So one has a bar under it, the other one does not. So the way you can remember which one is which one is subset of is kind of like less than or equal to. Okay, so the left hand side and the right hand side can be the same and the operator will still return true. Proper subset of is more like less than. Okay, so let's pick out how it is defined. A is a proper subset of B if and only if A is a subset of B to begin with, and B minus A is not empty. Something in B is not in A. Is that okay? All right. So do we want to look at this a little bit more, or are we ready for what conditions will fail that? All right, so what we'll do is we are going to, okay, I'm going to put this at the bottom of the screen just so that I can have the text editor on the top, and I'm going to reuse these examples. So instead of just a subset of, there will be proper subset of. Okay, so copy, paste, and let's see, I think there are four of them. Yep, there are four of them. So select this whole portion, and we want to do a search and replace. There we go. Find and replace. So we want to change subset to proper subset. And match case, match whole word, regular expression. I don't think I need those fancy stuff. Replace only in the selection. There we go. Doesn't look like it got it done because nothing is selected. What's going on? Okay, try it one more time. Aha, cool. All right, so we're gonna take out all the original answers and then we'll try to figure out the answers again. All right, is the empty set a proper subset of the set that has ABC in it? Well, first of all, is the empty set a subset of the set that has ABC in it? Okay, so a yes on the first one. What about the second one? Is there something in ABC that is not in the empty set? They're all in ABC. Everything in ABC cannot be found in the empty set because that's kind of the special thing about the empty set. So the answer is yep. Okay. And what about this one? Is the set ABC a proper subset of itself? It is not. Very good. Because it is going to fail this condition. Because there's nothing in a set that is not found in itself. That just doesn't sound right, right? Correct. Yep, for the most part. Yep. All right, so for the third one, this is a false because AB2 is not even a subset of ABC to begin with. So the second condition does not even apply. And then this one is true here as well because C is found in ABC but not in AB. All right. So do we have any questions about the this is called a relational operator because it relates A and B in a certain way, and then it just tells me whether it is the case or not. So do we have any additional questions about proper subset of? Okay, I'm not seeing any questions about that. Then we're going to move on. So that's about it. I mean, this is all we have in the simpler example or simpler explanation. So we're going to close this one and then go back to the hair splitting one. So with the hair splitting one, it introduces the concept of a predicate. So P of A is a predicate. So when P is a predicate, it is just a function that returns true or false. Is that okay so far? I'm skipping a bunch of stuff from the beginning because we talked about those already. So now we are introducing quantifiers, which is actually in one of the deprecated ones too. So quantifiers are super important in this class. So this one looks like an inverted A. It is for all. So the way we read this particular expression here is for all E, P of E is true. If you want the quantified expression to be true, then for everything E, for each thing E, P of E has to be true. It is a universal quantifier. If that sounds a little bit abstract and it sounds really weird, it's easy, okay? Because every time you see the inverted A, all you have to say, oh, it means the same thing as every, okay? So every is a universal quantifier, okay? So now we can take a look at an example, okay? So we're going to focus on this example here and ask, why is that true, okay? So it says for everything in the entire universe. So that means I can also be my car, it can be you, it can be me, everything in the universe. Okay? So there's no restriction as to what I can bind to because it has to bind to everything in the entire universe, including the constant pi, the constant e, and so on and so forth. But the actual predicate is this one here. In other words, we have to evaluate this expression and see if it is true for every I that is imaginable in the entire universe. Is that okay? So now we're going to pick some really absurd value for I. Okay, so we'll say, okay, since Iraj is one of the things in the entire universe, so I can bind to Iraj. So you have to ask the question, Iraj is an integer implies Iraj is a real number. Okay, that does not even make sense, okay? Because Iraj is a person, not a value, not a numerical value. But you can still answer the question. Is Iraj an element of the set of all integers? You can still ask that question. It's a stupid question to ask, but it definitely has an answer of either true or false. So you tell me, is Iraj an integer? False. Okay, very good. And then you ask, is Iraj a real number? False. So now what do you have? You have false implies false. Do we know how to evaluate that? It is true. Okay. So when I binds to Iraj, which is one of the many things in the universe, this is true. What about when I is tech? The whole thing is going to be true again because for anything that is not even an integer, the implication is going to be true. Does that make sense to you? Okay, now it should make sense once you understand what implication does and know its definition as a truth table. Because whenever the left-hand side of the implication is a false, the implication itself is true. When did we learn that? Exactly. So I'm going to emphasize that until people get irritated enough and go, fine, I'm going to study before class. But in the end, is it helping me or is it helping you? I'll leave it to you guys to answer that question. All right. So now we can focus on, oh, okay, so anything that is not even an integer, this implication is just going to return true. So that means it doesn't make sense to ask those stupid questions anymore. Okay, so let's focus on just integers. So let's pick 25. Okay, so 25 is an integer is true. 25 is an integer is a real number. That is also true. So now you have to say, okay, so it really is asking if I'm already confining my consideration only to integers, I'm asking is an integer automatically also a real number? That's what it's asking. The answer is yes. Okay, so that means this universally quantified expression is true because it applies to every thing in the universe. For things that are not even integers, this is automatically true. For things that are in fact integers, this is guaranteed to be true as well. So that is how we analyze this particular expression. Are we doing okay so far in terms of how to interpret that expression? All right. The next quantifier is there exists. Okay, so whenever you see the um, left, right, reverse, symbol E, it is exist. Okay, it's basically says there exists an element or a value in the entire universe such that P of E is true. So that sounds really awfully abstract, right? So now we will convert this into things that we are more familiar with. When you see the inverted A, it is every. So when you see there exist or the kind of reversed E, it is the same thing as some, SOME in English. Or better yet, at least one. Is that okay? So if you are one of those people who prefer the more colloquial way to refer to the operators, then now you know how to map these symbols too. Okay, so now we're going to look at this uh, statement here. So this statement, or in the example, this is a statement. It is quantified, but it has a value of either true or false. So let's check out what this is asking. So there exists something I in the entire universe, such that I is an integer, and I is greater than 0, and I is less than 1. Okay, so what do you think is, I mean, obviously I worked this out already, but why is it false? What about 2.5? I mean, not 2.5, but 0.5. Well, 0.5 is in the universe, okay? It's a value. It exists in the universe. It is greater than 0. It is less than 1, but it is not an integer. And because everything is ended together, if at least one of these is false, the whole thing is false. You're like, okay, what about 0 itself? Well, 0 itself is an integer, but it is not greater than 0. So it fails this condition. What about 1, the other end? Well, 1 is not less than 1. So it fails another condition. So there's nothing in the entire universe that can make all three parts true for this conjunction. And therefore, the quantified expression itself is also false. Is that okay? So without quantification, and I just give you an expression, then it will be ambiguous because you can interpret that as, hey, can you find at least one value that can make this true? Or am I really asking for every possible value, this has to be true? So if I do not use a quantifier, then the question or the statement is ambiguous because you don't know whether I'm saying for everything or this has to be true, or am I asking, can you find at least one thing that can make this true? So that's the importance of having quantifiers because now I can be very clear, whether I'm saying universal, like for everything, or whether I'm just talking about, oh, I just need you to give me one example, and that's enough. So are we understanding the importance of quantifiers? All right. It's just like in normal English conversations. If you think, okay, we cannot use quantifiers anymore, okay? And you say, professors are cool. Then I'm asking, are you talking about all professors? Because I certainly know people who are not cool and they are professors. I just have to look in the mirror, okay? Or are you asking, is there at least one professor who's cool? Well, that would be Iraj. So the answer would be different depending on whether it is a universally quantified expression or it is a existentially quantified expression. So the for all thing, which is at the top of the screen, that is also called a universal quantifier. The um, reverse E quantifier is also called an existential quantifier. Is that okay? All right. So now we are going to use those to define operators that we have encountered already. And you can see that, oh, that looks exactly the same as the other one, except now it has a quantifier in front of it. But that is important because without the universal quantifier, we might understand that is what we meant, but it is not explicit. But now it is explicit. Is that okay? Because if I were to change this universal quantifier to existential quantifier, then that means, oh, the intersection between two sets only has to have at least one element that is common to the two sets. Everything else we don't care. That would not be the proper definition of intersection because with intersection, it has to be a universal quantifier. Are we good so far? All right. And then the same thing with union. So there's nothing, different about the other one. And then the difference is kind of the same way. So when we get to subset of, oh, this is a really interesting and easier way to define subset of. So X is a subset of Y if and only if for everything in the entire universe, E is in X implies E is in Y. So that is another way to define subset of without using difference and intersection. Does that make sense to you though? Well, let's plug in the examples that we have worked out already and see whether that works or not. And also see mechanically how do we do this. So we're only looking at subset of, right? So we're going to go back to just this one first, okay? So the question is, what is the outcome when you evaluate, this expression here? Or to be more exact, we only care about the right-hand side of the if and only if, because the left-hand side is just the definition of the symbol. So now we say, okay, for everything in the entire universe, okay, let's choose Iraj again. Okay, so we are saying Iraj is an element of the empty set. False, not true. Oh, but that automatically makes the implication true. Okay, so it's the same mechanism that we have seen before. E is in X is really just a filter. It basically says for things that are not in X, don't even bother to see if it is in Y. Is that okay? So what if X is an empty set? Because in the example that we are actually examining right now, X is on the left hand side of the operator, and in this case, X is an empty set. So if X is an empty set, what about this expression, something is in X? It is guaranteed false. That's right, because nothing can be in an empty set. So if nothing can be in the empty set, the implication is automatically true. Oh, okay, we're done. Are we doing okay so far? So that's how we think about these operators. There are always several ways. Okay, I shouldn't say always. That's a quantifier as well. When you say always, it's a universal quantifier. Okay, so there are many times there are multiple ways to look at the same thing, and we are just witnessing. Oh, we can define, subset of using the set operators, but we can also use quantifiers and just element of, and in some way this is actually easier to understand. So if that is subset of, what about proper subset of? Let me just try. I'm trying to scroll to the right point. This is good enough, I suppose. So now we are asking about proper subset of, and we're going to pick a really tricky case. Okay, we're going to pick the one here. ABC is a proper subset of ABC itself. We already know the answer is supposed to be no. So now we look at this expression here and go like, why is it false? All right, so since ABC is the same as ABC, X and Y are really the same thing. Okay, so the first question is X a subset of Y? Yes. And ah, now we have the quantifier. The quantifier is asking, can I find at least one thing out of this entire universe such that that thing is in Y but not in X? So we look at, okay, what about tag, right? Tag is in Y and tag is not in X. Well, tag is not in Y, you know, because in this case, Y only has ABC in it. I'm not in that set. So tag is in Y is false, which means the entire conjunction is going to be false. So you look at all the things, and then finally you settle on, oh, what about, well, you look at everything in the universe, including the value A. So you plug in the value A. A is in Y. We good? But A is not in X. Ah, it is also in X. So that means the left-hand side of this conjunction is true, but the right-hand side of the conjunction is false. So we have true and false, which is still false. Yep. Okay, so I need to differentiate what you mean by this and that. Yes. hmm Are you referring to this statement? So instead of using this statement, you're referring to the other way to define a proper subset of? Well, the proper subset of still relies on element of, which means you still need a loop of some kind to see if something is in a set or not. So you still cannot avoid the control structure part of it. Yep. It depends on your implementation, of what a set looks like, but you still have to implement difference in that case, right? So how do you implement difference? Well, guess what? You still have to go through loops. So for everything on the left-hand side, you have to say, oh, is it also on the right-hand side? Well, guess what? That's a loop. In fact, it is a double loop because you have to look at everything in on the left-hand side, and then you have to compare that to everything on the right-hand side and see if you have a match or not. So it's say again. These are useful. It's I think is to me it is just one way of looking at the operator, your proper subset of in this case. Yep. Well, we'll see in hopefully in today's lecture, we'll see how um, the quantifiers, how they actually relate to conjunction and disjunction, because there's actually a very close relationship between those two. In fact, let's do that. Okay. Formulas? What do you mean by formulas? Behavior. Okay, then it's okay. I mean, if you once you find out, how to express it, because I'm not quite understanding what you're referring to, so I can't like an algorithm. What about? Hmm. Well, it depends on whether a set is a built-in type or not. What you can do with a set object. So for the most part, if you have if the language has the tool to express stuff like this, then you can do it. Okay. Um, I can tell you that JavaScript actually has these things. If you use an array, it has a method called sum and another method called, I'm not sure what, I think it's every. Okay. But it has quantifiers, quote unquote quantifiers as methods. Uh, well, we are not terribly interested in algorithms in this class. We will do some algorithms in this class, but for the most part, we are only interested in expressions. Is it true or not? But it does have a relevance. Okay, we're gonna get to it when we get to functions. Um, how do you describe the proper output of an algorithm? That's kind of the general question. How do you do it? So I'll give you an example. Okay, the input of the algorithm is a general array of integers. Okay, that's fairly simple. Okay, the output of the algorithm is supposed to be the sorted version of that array of integers. Is that okay? So to most people, and hoping for the everybody in this class, the concept of sorting is easy, right? We know what it is about. But how do you describe it mathematically? In other words, you have all the inputs, okay? These are the initial values in the array. What is the mathematical expression to show that, oh, if the output fits this requirement or make this statement true, then the algorithm is doing the job correctly. So that is the question, okay? As it turns out, just to express the array is sorted is not simple, not even close to simple. We have to get through all this stuff. We have to talk about functions. We have to talk about bijection before we even have the vocabulary to say, oh, if the output of this algorithm makes this condition true, then the algorithm has done what it is supposed to do. But why is that important, especially in the day of, oh, I can just vibe code. I don't need a computer science degree. Yes. Mm, are you talking about the expression that is so we'll get to that, okay? I think you're okay. But that's exactly the problem with vibe coding. I'm not expressing it well. So if you're not expressing it well enough for me to understand, do you think the AI will? Exactly. Yep. That is the problem of vibe coding. People who are doing vibe coding, the ones without a degree in computer science and have experience writing code, they don't know what to say. They will give the AI some really vague description of what they want to do, but it may not be precise enough. It may leave out a lot of assumptions. Now, one thing that GPTs are not very good at is to go like, okay, what you just told me is a little confusing. What does it mean when people say it's confusing? It's not the same as not understanding. Confusion is not understanding. Confusion means, so let's say you guys tell me something, okay, and I say, okay, that is confusing. What does it mean when I use that word confusion? It means I understand what you're telling me, but I can have 16 different ways of interpreting what you just said. I do not know which one out of the 16 you actually meant. I need you to clarify. That is confusion. Okay? So for me, I will come back to you and go like, okay, you just told me about something that you want to do, but it's not clear enough to me what you mean. Okay, and I have all these different ways of interpreting what you said. I will come back to you with that question. GPTs do not. So what would GPTs do? Well, out of the 16 ways of choosing the next token, they all seem like they have about the same probability. I think I'm just going to throw a dice. That is what GPTs do. It doesn't come back and ask for clarification when there are multiple tokens of about the same probability of being chosen as the next token. It doesn't detect that condition to begin with. So that means when you specify something that is confusing to the GPT, it will just randomly pick one of the choices and move on. It won't come back and ask, okay, got several ways to interpret this. Which one do you mean? Okay. And that is one limitation of vibe coding is the GPT doesn't come back and ask you, what do you mean by blah, blah, blah? It just go like, I think I can make an assumption about what you meant. And I'm going to move on with that assumption without letting you know what assumption I have made. Do you want an employee to work like that under you? So understanding the limitations of GPT is really important to you guys. Not so much to me, because I'm going to retire in a few years. And for what I do, it is not that big of a deal. But for you guys, you have at least 2 more years before you graduate with a bachelor's degree. So that gives Moore's law one more cycle, which means by the time you graduate, the computers, the GPUs, will be twice as powerful. Or you can say the power consumption is only going to be one half what they are now. What they are now. Mass store is going to be half the price of what they are now, and so on and so forth. So you kind of have to plan for that to happen. So what I'm telling you about the limitations of GPU, I mean not GPU, GPTs is something that you can hold on to and just go like, okay, so now that I know the limitations, so my value as a software developer is not just that I can write that code, but I know how to specify what is the correct output of this code. Now, if you can express that really well, I can go like, well, maybe GPT is capable of generating algorithms and test those algorithms and only give you the ones that work. Maybe that's possible. But until you can express what it means to be correct as the output, then all bets are off. Okay, from my perspective, all bets are off. So I know I just digress a little bit, but I think it's important to kind of bring those topics into the class. All right, so let's take a look at this one here. Okay, because we actually talk about this too. This is a notation, of how do we specify membership in a set when that set has an infinite number of elements? Okay, so we talked about exactly this notation in a different way. So this is a definitive way of defining what is in the square box or inside the rectangle. So let's read the whole thing. For everything in the entire universe, okay, for everything E in the entire universe, E is in this particular symbol, okay, it's just a symbol in this case, if and only if P of E, which is predicate P applied to E, is true. Okay, so without the explicit comparison to true, it just means this has to return true. So this is the other way to define this notation to say, oh, okay, so everything that makes P true are in the set. But if something is in that set, it also is guaranteed to make P true as well. So this is the other way to define the notation that we have already gone through the other day. Let me show you what I mean by that, because I think it is kind of important to relate multiple ways of defining the same thing. It's not in this one, I believe. Oh, okay, I might have closed that one already. Right. Okay, so I think I know where to find it. It is in this particular module and a set that has an infinite number of elements. It's right here. Okay, so before I introduce quantifiers, I basically say if E is defined to be this symbol here, it simply means everything in E is, okay, I shouldn't say that. X is an element of E if and only if P of X is true. But I didn't use a quantifier. So that means, somebody can mistake this and go like, maybe you meant existential quantifier. So if I can find one thing out of the entire universe, X, and kind of evaluate this way, that would not be the same definition as what it's meant to be. Okay, so this is one way to define it. And then the other way is this way. So they really are meant to be the same thing, but this is a more precise way of defining the notation of we have a set where each element E in the set makes P of E true. We doing okay so far? You mean what is in the box here? The entire expression? Okay, so this is how we define this notation. In other words, look at everything inside the rectangle as blah. Okay, so this means for everything in the entire universe, a thing is in blah if and only if P of that thing is true. That's basically what it's saying. So that means this, okay, use a mouse pointer. So that means this entire thing, this if and only if expression, is only here to define this symbol here. The entire thing inside the box is a symbol to mean, oh, we have a set that has a whole bunch of stuff. Everything in this particular set has to make the predicate P true. That's it. All right, so we got 3 minutes. I am going to introduce you to a even more confusing, but it's not actually confusing because we have a very definite use of confusing itself in this class. In other words, the word confusing should not be confusing. There's a very precise definition of confusing here. So what I want to introduce you to is this module here. All right. So this module talks about some summation or the sigma notation first. Do we have any questions about the use of the sigma notation? So everybody is somewhat familiar with the sigma notation. But if I were to ask you to describe what the sigma notation does, that gets a little messy, okay? Because you kind of have to go into the loop concept or something like that. So instead of using that, I use a recursive definition to define sigma. So this is the recursive definition of sigma. So it goes like, okay, sigma, I goes from B to E of f of I. In other words, f of I is just a function that returns a value that you can add to the f value of all of the other things within the range from b to e. Okay, so the way I define this is to say, hey, if the beginning index is greater than the end index, just return a zero because there's nothing to consider in this case. So if there's nothing to consider and you're adding stuff together, it's just a zero. Okay, so this is the base case. The recursive case is when b is not greater than e, which means b is less than or equal to e. If b is less than or equal to e, I can always count on b being inside the range, and I'm going to evaluate f of b as one of the things that I have to add. Is that okay? So I'm going to add to this whole thing the recursion here. The recursion is, oh, let's just bump the beginning index from b to b plus 1, because guess what? I just took care of the case when I equals to b. So the recursive call is to say, let's start with the next number and do this whole thing. And then you just reevaluate the whole thing recursively. Is that okay? So I just defined sigma or summation without the use of loops and all the other kind of more vague terms, because it is definitive. It's done. So what does this have anything to do with this class? What it does have to do with this class is the for all symbol. Where is the for all? There we go. Okay. So this is the existential, quantifier. So the existential quantifier can be re-expressed as a big or. Okay. I'm still missing one concept, which is the filtering, notation. So I cannot really kind of get into this, but it suffices to say that the existential quantifier really expands to a gigantic or. The universal quantifier expands to a gigantic and operation. Because in order for a universally quantified expression to be true, that condition has to be true for everything in the entire universe. Wait, did I just say that it has to be true for everything? Isn't that what conjunction does? And then with the other one, I said, hey, give me at least one thing that makes this entirely true, that makes this entire expression true. What is going to do that? Disjunction. Okay, because if you have a gigantic disjunction, and of those many things inside the disjunction, oh, this is the only one that makes it true. Well, guess what? The entire disjunction is going to be true. So that's the connection between the logical operators and or versus the quantifiers. Okay, so you can see how things are actually connected. A lot of these concepts may not seem connected, but in reality, they are actually all connected. Okay, being able to see that connection is, I think, is helpful. I think it's important. So that's it for today. And what we are going to do is, let me see if I have covered enough concepts to do the set homework. I think we have. So I will release the set homework assignment. Okay, there are a few. So I will release one, and then there's another one that is a little bit harder, and that will be done later. So I am going to release set notation. This one. Um, the date is not set yet. Okay, so I'm gonna do it later. So let me just kind of unhide it, and I'll do it now. Next Monday is a holiday, so I won't see you guys until Wednesday. So that means our due date is going to be the 3rd, and I'll make it right before class. And as far as reading is concerned, just continue to read. Okay, the next topic is functions. So once all the set notations are done, the next topic is this one, which is functions as sets. Okay, so if I were you, I would try to read at least a portion of this before next Wednesday, because this is the this kind of stuff is not difficult if you keep up with the class in terms of the notations. I think what makes this class difficult for some people, it has to do with the notations. So if you keep up with the class in terms of the notations and you're familiar with, oh, okay, this means this, and you'll be familiar with all the notations, keeping up shouldn't be too hard. Okay. So I will probably send you guys something, over the break, or over this entire week, just so that, you have something to do, keep your mind on the topic, keep the engine warm, so to speak. Okay. Because you don't want to start with a code engine on next Wednesday and go like, I have no idea what these symbols mean. That would not be good. The AI can also be useful. I know you guys can go if you want to, but you can also use the AI to help, ask you questions. Okay, you can always ask, okay, ask me some questions about such notations, just so that I can confirm my understanding. So you can always do that. Alrighty. So I will see all of you next Wednesday. Have a nice weekend. It just sounds really odd to say have a nice weekend on a Wednesday, but that's reality. All right.